So we're going to use this problem, which is an inelastic collision. We know this, by the way, because they collide right here and hold on to each other after the collision. That's inelastic. It is between two individuals, skaters, because we're trying to ignore the external force of friction here. And the trick here, well, one of the keys to this problem is that it is, in fact, a two-dimensional problem, but it is a pretty simple one. So, you see momentum, you want to look at initial and final situation. Initially, we have one skater going to the east. We'll say that's to the right. And we have another skater going to the south. We'll say that is down in this case. So we're looking at them, say, from above. And they give us enough information, as you'll see here, to find the momentum of each skater. Now, this is a two-dimensional problem because their two momenta are at right angles to each other. So you can't simply add 64.4 plus 277.2. They're not in the same direction. Or you can't just subtract them because they're in opposite directions. That's not the way this works. If they're at right angles, two distinct dimensions, then we really are at the point where we have to add them using Pythagorean theorem, like we've looked at many times for vectors. So, for example, let's create this. We go here. Let's see, and let's change the color of that. We'll go with purple. There we go. There you go. Now, we have a we can create this rectangle where this side here, of course, is the same length as this momentum of the person going east originally. And this line here is equal to the momentum of the person going south originally. And the overall answer to this problem, or the sum, or not the answer, but the combined, let's find a good arrow here, the combined momenta are going to be an arrow that goes from the origin to the diagonally across that rectangle. So, for example, we'll do orange. So this is going to be the actual momenta, or momentum, prior to the collision. Now notice, you wouldn't see anybody moving in that direction. This person would be going to the right, this just before they collide, this person would be going down, but when you add their momenta, it would actually be this orange line that you see here. Now, we can find that number. That's not hard to find at all because it's really just a right triangle. This is one leg, this represents the other leg. So for example, this length here is the 64.4, and this length here, well, actually, let's do it this way. This rectangle right here. So I'm going to shade that or highlight that. Let's see if I can highlight. There we go. Let's see what happens. So I'm going to look at this triangle here. From there to there, and then back along here. I'm going to look at that triangle. Because that triangle, I believe, is going to be a little better for me because I'll be able to talk about this angle, which is the reference angle. So I know this side is, of course, the 277. That's this side. And this side of that triangle is the 64.4. So the hypotenuse, of course, is going to be the one side squared plus the other side squared, and then take the square root of that after you add them together. Now, let's see. We don't want to use that. So I'm digging for a pen. There we go. So I'm going to have the overall momentum before the collision The initial momentum is going to be the square root of 64.4 squared plus 277.2 squared. And you get that number. Now, let's say this again. That is this vector. That is the momentum before. Well, since the forces are all internal between the two objects, what does their momentum afterwards have to be? You got it. It's got to be the exact same vector. In fact, here, we'll even draw it with the same. It is going to be, get rid of that. There we go. Is going to be the exact same vector because the momentum before has to be the same as the momentum after. Now, what makes this problem easy, and in fact, dangerously easy, because chances are, if, for example, you did what I showed you to do right here, you'd be like, oh, hey, I got this number. Okay, well, I got the momentum and I could divide by their mass. But you may get an answer here just by accident and not even know. But what the truth here is that after they collide and they stick together, now they will go in this direction because they're all one object. And if the momentum of one object is given as a vector, the momentum they have to be moving in that direction. So whatever we found as our momentum here is our momentum finally as well. Now that's going to be, well, what's that going to be? What's another way to look at that? That would be the total mass, because they stick together. So the mass of the east person plus the mass of the south person times their final velocity. And since they're stuck together, they only have one velocity afterwards. So we would have found this number, which is the same as the final momentum. If you divide by their combined masses, you'll have the final velocity. What about this angle? Well, if we remember where it came from, so we'll have to erase some stuff here to make it clear. If you recall, that's this angle here. And that's going to be opposite over adjacent. That's tangent. So that angle, that reference angle, is the inverse tangent of the momentum of the south person divided by the momentum of the east person initially. And from that, you'll be able to get the angle, this angle right here. Now, I want to take this a step farther. What if the problem started off like this? This is a slightly more complicated problem. Can we get the final momentum in this situation? So in this one, just before they collide, the person who initially was going east, I'm still going to call them east, but it isn't all east, is it? If you look at that, that person is no longer just moving east. They're actually moving northeast. So when they go to hit, here's that one person, and they're moving this way, and the other person is coming at them and moving this way with a larger mass and more velocity. So when they hit, at the moment they hit, this is what their momenta look like. This one's down like this way and large, and this one's much smaller and up in that way. So, before I can even consider getting the total momentum here initially, I need to get their components. And the red vector, the one that's straight down, that's already in the y dimension and no x, that's no big deal. But this one has an x component and a y component associated with it, and I need both of those. So this problem is going to involve some extra steps. I need, still calling them east person, even though I know they're east and north, their original x momentum is going to be their momentum, mass of the east person, initial velocity of the east person, times the cosine of this reference angle that they give me. And this component here, the vertical component, is going to be POY, is going to be mass of the east person, velocity of the east person, times the sine of that 38. So down here, I'm going to take it another step. I'm going to actually just draw the components. Something like that, and I'm actually going to get rid of that. So I have original of the east person, their y component, would be whatever I get when I multiply all this stuff together. We can do that. So if I remember correctly, that was 46 times 1.4. That was their mass and their velocity. Times, now that they're moving at an angle, the cosine, no, the sine, we're doing the y, sine of 38 equals, so 39.6. So this is positive 39.6, right, because it's upward. Although maybe we'll put the negative and positive in later. Oh, here. I already have a spot for it, don't I? 39.6 kilogram meters per second. Now, what about the x component? Well, that's going to be what we talked about above. So it's going to be, let's bring up the calculator. And we're going to do, I believe it was 66 kilograms times 4.2 meters per second times the cosine of a 38. That's going to be 218.4. Now, and that's going to be to the right. Meanwhile, this person, well, this one's not changed, right? Because we didn't change its angle. It's all in the y. But we have to look at, for the initial, we have to look at it in two dimensions. So what was the net momentum, for example, in the x? We'll start with the easy one. Well, take a look at your diagram. What are the momentums in the x? There's only one of them. It's just POEX. It's the original x velocity, x momentum of the person who is, called the east person. So that's just going to be 218. Whoops. Did I switch those two? This is wrong, isn't it? Did you spot it? There's no way that's 218, right? I used the other person's mass and velocity and stuff. So let's get rid of that. I mean, 218, really? How the heck did that happen? So let's fix that. So we're going, and we're still, the east person is still 46. They didn't gain weight. So 46 kilograms times 1.4. Notice I had switched to the other person mistakenly. Times 38, and now cosine equals, there we go. So I got 50.7 for that one. I feel much better about that now. There we go. So that's all right. So that's 50.7 to the right. We'll call that positive for now, but I don't think it's going to make too much of a difference what we call it. Over in the y dimension, though, what's the net momentum in the y originally, before the collision? Well, upward is this. Downward is this. So I have 39.6 minus 277.2. Or if I was going to write it out in symbols, and let me give myself a little more space. If I was going to write it out in symbols, I would write the net momentum in the y before the collision is going to be the upward one by POEY minus the one that's down. So momentum of the person moving south originally. I'll say y, but it's all in y anyway. There's no x component for that one. Either way, I'd have to subtract the two. So I'd have to take 39.6 minus 277.2. Negative 237.6. So what we're looking at is, when we're all said and done, is we are looking at a momentum, there we go, in the x of, what we say was 50.7, and a momentum downward in the y of 237.6. Now it's very similar to the problem we were looking at a moment ago. We have an x component, a y component, and we need the overall, and that's going to be, so the initial momentum overall is going to be the square root of the 50.7 squared plus the 237.6 squared. That will give me this. And then the rest of the problem is just like the other one, for example, if you were solving for the same stuff, because then you'd know, if you know this is the original momentum, that has to be equal to the final. And you could use their, since they stick together, you could use their combined mass, divide by that, and you would find out how fast they're going. But it's a more complicated problem when you have one of the momenta is at an angle, because you have to break it up into components and then combine the components, just like you would find net force or something. It's very similar to that since it's a vector, same process.